Hi there, everybody. We're going to take a look at our week 8 material here. Week 7, we looked at the normal distribution and the continuous probability distributions, but we focused on that normal distribution and the bell curve. Today, we're going to look at the next step, where that normal distribution or that bell curve gets applied to sampling distributions. So we're going to look at constructing a sampling distribution, and then we're going to get into the central limit theorem. So what is a sampling distribution? Well, a sampling distribution is literally that. We are taking samples from a population. And we're going to give some examples here in the slides in just a little bit. But let's say you take the ages of you and your 3 best friends. So you have 20, and I'm going to put them in order from smallest to largest. 25, 26, 29, and 35. So those are your 4 ages. And let's say I want to take samples of size n equals 2 out of there. Well, I can actually take, if I assume I can repeat numbers, I can actually take 16 different samples of size n equals 2. If I assumed I couldn't repeat, it would only be 12 samples. So anyway, if I take all of those possible samples of size 2, in other words, all the different pairs of your ages, and I find the mean, so I got 25 and 26, there's one possible sample. That would give me a mean of 25.5. I might have 25 and 29. There's another possible sample. Taking those two. Well, if I average those together, it gives me a mean of 27. So I take all those samples and find all those means. My sampling distribution are the sample means. It's the means. So that's why it's called the sampling distribution of sample means. So what we're doing is we're involving, as I said, sampling. Statistics is about taking samples from the population. So what we need to be able to do is we need to be able to relate those samples and the statistics we calculate from those samples back to the population. So we need to know how those samples, because usually we're looking at a mean of those samples, or in the next section we'll get a proportion of those samples. We're looking at the mean and comparing it to the mean of the population. So we need to know how those means in those samples will vary in relation to the mean of the population. I mean, the population mean is set. I mean, it's not going to change. Those samples, however, it is possible that we take samples that have means slightly less or slightly greater than the population mean. Now, we talked about a lot of stuff in the first couple of weeks about taking good samples to guarantee that, or try to ensure at least, not guarantee, but to try to make sure that our sample has a mean as close as possible to the whole population. I mean, a good sample, the better the sample, the closer the population its mean will be. But it's never going to, it might not always be right on. It may be, but it usually will not. It's still going to vary a little bit. So the sampling distribution describes how those means of those samples can vary around the population mean. So what we're looking at is, like I said, we're taking several samples from the population. In fact, we're picking a size of the sample, and we're taking every possible sample of that size out of the population and calculating the mean for each sample, the x bar. And it's those x bars now that are actually going to form a distribution. And it is going to form a bell-shaped curve. A couple of requirements there. One is that the original population has to be approximately bell-shaped or approximately normal. If it is not, well, then the sample size has to be 30 or larger in order to assume that. So because the value of x bar varies each time a sample is taken, and not every sample is going to have the same mean. It is a random, now x bar is going to be treated as a random variable. Now, how is this going to compare to the individual values for the population? So let's say here is our population, all the individual values, the distribution of all the individual values. Well, I take this sample mean, and of course I take my sample, I should say, and find its mean, and the means are scattered all over, so I'm going to graph those sample means. Of course, there's going to be less of them than there were, and that curve is also going to be narrower. Because let's face it, in the whole population, if I'm selecting an individual value, it's relatively easy to find one value that's really small, or randomly select one value that's really small, or randomly select one that's really large. But if I'm selecting several values, chances are, if I get a small one, I'm also going to get a larger one that's going to cancel it out. And the mean of those values is still going to be closer to the center of the curve, so closer to the mean of the population. So that distribution of population means that sampling distribution should have the same center, but it's going to be a lot narrower. And how narrow it is depends on how big the sample is. The bigger the sample is, the more likely that any small values are going to be canceled out by large values. So anyway, that is our sampling distribution. We can also deal with it as a probability distribution. And we'll see that towards the end of this slide. So here's our example. We're going to take a tetrahedral dice. That's a four-sided die, numbered 1, 2, 3, 4. And we're going to roll it. So now our population are the values 1, 2, 3, and 4. We do some calculating there. We can easily find the mean is 2.5 and the variance 1.25. And of course, standard deviation is the square root of that. So now let's take a look at all of the possible samples of 3. I'm going to choose 3 values. Now again, I'm assuming here I can repeat values. So 1 can be chosen all 3 times, 1, 1, 2, and so on. I've listed out here all of the possible combinations of 3 numbers I can take from that list if I'm allowing myself to repeat. It ends up being, what, like 81 of them or something. Or 64, actually. Sorry, there it is. So anyway, what we've calculated then for each of those samples of 3 is we found the mean of that sample. So this right here, these means, that is our sampling distribution, is those means. So now we're looking at those means and how they distribute, what type of curve they make, what the mean of those means is, and what the standard deviation of those means is. So here, the mean of the sampling distribution is denoted by mu x bar. That is saying the mean, it's a mu and not an x bar because we took every possible sample. So it is the population of possible samples of that original population. So it is mu of x bar, means of the sample. X bar represents the sample mean. So it is the mean of the sample means is what that notation says. And it should be equal, well, if we took all of the possible samples, it will be equal to the population mean for the individual values. Remember, this is for individual values. So of all the individual values in the population and find their mean, it'll be equal to the mean of all those sample means that we found. The variance, we said it's going to be narrower than if here's our population curve, the curve or the distribution for the sample means is going to be narrower because the small values cancel out the larger values and so on. And we said the bigger the sample, the more likely they are to cancel out, the narrower that curve is going to be. Well, this is describing that here. The variance, and this again is the variance, the sigma squared of x bar. So the variance of the sample means is equal to the variance of the population divided by the size of the sample. Since the standard deviation is the square root of the variance, we square root all that. So this is the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. This is just summarizing what we just said. The big thing, of course, the mean of the sampling distribution, the mean of the sample means should be the same as the mean of the individual values in the population. Standard deviation of the sample distribution. So the standard deviation of those sample means is the population standard deviation for the individual values divided by the square root of the sample size. The term you'll hear me say a lot, standard error of the means, is sometimes used to describe the standard deviation of the sample means. So let's look at an example. Among students at a certain college, mean number of hours of television watched per week is 10.5. Standard deviation is 3.6. Random sample of 16 students is chosen for study of viewing habits. Let X bar be the mean number of hours of TV by the sample students. Find the mean of the sample means and the standard deviation of the sample means. Well, the mean of the sample means should be equal to the mean of the individual values. That's just 10.5. Standard deviation of the sample means. Well, you're going to take the standard deviation of the population, 3.6, and divide by the square root of the sample size. Sample size is 16, so square root of 4. So 3.6 divided by 4, or 0.9, is the standard deviation of the sample means, or the standard error. Using the central limit theorem. So now that we've defined this distribution, it has a mean here, which is equal to our population mean, and it has standard deviation, which is just our population standard deviation divided by the square root of n. We can use that mean and that standard deviation to find normal probability, since it's approximately the normal curve. So recall the tetrahedral dice, we had the population was 1, 2, 3, 4. Probability rolling each number on the die is the same, 0.25, assuming it's a fair dice. So each number has a 1 on 4 chance of being in the result. So that is not a normal distribution. This is what we call a uniform probability distribution. But anyway, when we take our samples and find the means of those samples, if we plot them, we get a bell-shaped curve. So this is showing you that even though the sample was not normally distributed, the population, was not normally distributed. The population was actually uniformly distributed, is the name we call that. It is flat across the top up here. Because there's more than 30 samples we took, the population or the distribution of those sample means still ends up being approximately normal, bell-shaped. Because it's bell-shaped, we can use our normal probabilities with it. So now, this probability distribution is very skewed, extremely skewed. Looking down here, though, if we took samples of those numbers, now again, the probability of randomly selecting 0 is 0.6. So there's a much better chance of selecting a 0 than there is a 4 in that distribution. If we take, this is saying a sample size of 3. If we take samples of size 3, we still get a skewed distribution. Not quite as skewed as the original. The original is actually just a inverse logarithmic distribution or inverse exponential distribution there. This one's not quite as skewed. If you take sample sizes of 10, it's just a little bit skewed. It's almost disappeared. The sample size of 30, it's nearly perfectly normally distributed. So as we said, if we get even if the population is not normally distributed, if we get a sample size of at least 30, that's the distribution of the sample means should still be approximately normally distributed. Remarkable fact is that distribution is that it is approximately normal for any distribution, whether it's uniform or heavily skewed or whatever, as long as the sample size is at least 30. No matter how skewed the population is, a sample size of 30 or more will make it pretty much normally distributed, really close to normally distributed. That's what our central limit theorem is stating, is that as the sample size is large enough, now basically, technically, I'm going to word it the technical way is, if a population is approximately normally distributed, or even if the population is not normally distributed, if you have a sample size of at least 30, then the mean of those sample means will be equal to the population mean, and the standard deviation, that's the mean of the sample means being equal to the population mean, and the standard deviation of the sample means will be equal to the population standard deviation divided by the square root of n. So, finding the probabilities, we make sure the sample size is greater than 30, or if we have a population that's already approximately normally distributed. Second, find the mean and the standard deviation. Well, the mean is just the population mean. Standard deviation, of course, is the population standard deviation divided by the square root of n. We can sketch the normal curve and shade what we want to find, and then use our calculator function to find that area. So here we have 2008, we have a mean of 25 years for students, standard deviation of 6.8 years. Simple random sample of 64 students, so n equals 64 here. What is the probability that the sample mean age of students is greater than 26? So the mean of our sample means here is 25, just the population mean. Standard deviation of our sample means is 6.8. That is our population standard deviation for the individual values divided by the square root of our sample size, square root of 64. Which gives us 0.85. All they're doing is repeating those calculations for us down here. The mean is 25, standard deviation is 0.85. Now that we have those, we can find the probabilities. So it asked us what is the probability that the randomly selected sample of 64 has a mean that is greater than 26. So here, the mean for the distribution is 25. So 26 is greater than the mean. It's over here. And we're looking at probability of being greater than 26. That's that area. So on the calculator, we're going to enter second variable, normal CDF. We're going to start at 26, go to positive infinity. I'm just going to use 999999, comma. We had a mean of 25 still. And our standard deviation was 0.85. We could also, by the way, I'm going to show you this in a minute here. We get a probability of 0.1197, which is what we're showing on our PowerPoint here. We could have also entered this way to save us a little bit of work and time. A lot of times finding that standard error or that standard deviation of the sample means is going to give us a really ugly decimal. So you can do this, 26, comma, positive infinity, our mean of 25, comma, our standard deviation, I was going to put in 6.8 divided by the square root of 64. Make sure I arrow out of the square root symbol, close my parentheses, and there it is. I get the exact same probability. And to me, that's easier to enter it like that, even though it's more calculator keystrokes, but you avoid that round off of dividing by the square root of n and getting some really long, ugly decimal number. So we get that probability being greater is 0.1197. We could find any probabilities now between two values if we wanted to, or less than if we wanted to. All we have to do is now make sure we're using the 0.85 for our standard deviation instead of the 6.8 for the individual values. Because if we're looking at a sample, the mean of a sample, its standard deviation is going to be the 0.85. So you do have to be careful. When you're doing probabilities now, are we looking for the probability of the mean of a sample being in a certain range, or are we looking for the probability of an individual value? So here, Hartford cattle are one of the most popular breeds of cattle based on data from the Hereford cattle, one of the most popular breeds of cattle. Based on data from the Hereford Cattle Society, the mean weight of 1-year-old Hereford bull is 1,135 pounds. The standard deviation, 97 pounds. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So it's saying, what's the probability that the sample mean is less than 1,100? Notice now my test statistic, or my statistic, and there's X bar, not X or Z. So the mean of my sample means is going to be 1135. That's just my population mean. My standard deviation of my sample means is going to be 97 divided by the square root of 100. Square root of 100 is 10, so it's going to be 9.7. So the probability of being less than 1,100, I'll put it in here. Second distribution, normal CDF. Less than be a negative infinity. So negative 999999. Or your textbook does -1. Then you do second EE 99 for negative infinity. Both of them work, and to me the negative 999999 is simpler to enter. I'm going up to 1,100 pounds with a mean of 1135. And my standard deviation, I can punch in the 97. I'm going to do this. Or 9.7, I should say. I'm going to do this. 97 divided by the square root of 100. Okay, so that's telling me 1.54 e to the negative 4. So that's 0.000154. The scientific notation when it does that, e to the negative 4 is 10 to the negative 4. So you got to move the decimal point over 4 decimal places to the left. So 0.000154 is a pretty low probability. I would say that is most likely unusual. They're drawing it in here. They found a z-score, but we did it on the calculator and got that right there, 1.54 e negative 4, which is definitely less than 0.05. So yes, it is an unusual value. Okay, so in this section we covered how to construct a sampling distribution. We did the tetrahedral die. We found all the possible samples and then calculated the mean of every sample. That is technically the sampling distribution is all the possible samples of that given size. So we can change the size and that will of course change the number of possible samples. Found the mean of the sampling distribution and how we equated that back to the population. How to find the variance and standard deviation. And then of course, central limit theorem stating your sample size is 30 or more. Then your sample means, the distribution of your sample means will be approximately normal. Then we use our central limit theorem to find probabilities. That is it for this section, this PowerPoint. So I'm going to switch to the next PowerPoint. Okay, so now in this section, we're still going to be looking at sampling distributions, but we're going to be looking at proportions now rather than means. So we're not worried about averaging together all the different sample values. What we're looking at is what proportion of them have a certain characteristic. So this is often used with qualitative data, categorical data. So if we have this proportion of the population, what's that going to relate to the proportion from each of our samples? So again, we're going to construct the sampling distribution for proportions, and we'll use our central limit theorem. So the sampling distribution for proportions. This can be very, very different. Get out of there. When we're doing our sampling distributions for proportions, because depending on our sample size, it is possible to get a whole sample that has this characteristic. So we can get a proportion of 100% or 1.0. Or it's possible to get a sample that none of them have that characteristic, so let's get a proportion of 0. So there's a lot more variation in our sample proportions. So here we have a computer retailer who wants to estimate the proportion of people in her city who own laptops. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. Turns out 35 out of 100 own laptops. That is a sample proportion. What we're doing is, let's say we draw samples, every possible sample from people in the city of 100 people. So it's going to be a lot of different samples depending on the size of the city. And find the proportion of every sample, and then find the mean of all those proportions. This is going to be the mean of the sample proportions. Now, for all the people in the city that own laptops, the proportion, that would be the population proportion. And we're going to be looking at relating the sample proportion to that population proportion now. In a population, the proportion who have a certain characteristic is called the population proportion. In a simple random sample of n individuals, let x be the number in the sample who have that characteristic. So the proportion, p hat, is just x over m. X is the number that have that characteristic. N is the total number of individuals in that sample or in that population. If it's a sample, of course, it's p hat. If it's the population, it's just p. In fact, some textbooks use pi to designate the population proportion. So the population proportion, in this textbook, they use just p to designate it. For the sample proportion, it's p hat. So if several samples are drawn from our population, they are likely to have different values of p hat because they vary each time a sample is drawn. Different amounts that have that characteristic, different amounts that don't. But we can relate, if we take all the different possible samples of that size and look at all the different p hats, that is our sampling distribution for p hat, or for p. And again, they're going to vary around. The population proportion is going to be at the center of that, but the sample proportion should be closer to it than the individual values are, because of, well, individual values would be 0 or 1. But you know what I mean. They should be closer to it depending on how big the sample is. So here we're going to flip a coin 5 times. N equals 5. So this is all of the possible samples of 5 we can take from the coins. You can see the sample proportion. If we're looking at the proportion of heads, well, here they're all tails, we got a proportion of 0. Here they're all heads, we got a proportion of 1. So those sample proportions do range from 0 to 1. So the mean of the sample proportions, as I said, is what we're looking for. That's the mean of the proportions. That is our mu p hat. Should be equal to p hat for the population. So the mean of all the proportions for the samples should equal to the population proportion. This variance, of course, is the variance of p hat, standard deviation of p hat, all describing that distribution. So here we go. Population proportion is 0.5 because that is the proportion that are going to come up heads. The mean of all those sample proportions better be 0.5. Now this is a little bit different here. The variance of the sample proportions is p times 1 minus p over n. So the standard deviation will just be the square root of that. So it's the square root of p times 1 minus p over n. So you can see it's narrower. The larger the sample is, the larger n is, the narrower that gets, the smaller that standard deviation of the sample proportions becomes. So in summary for that, this is our relationship, similar to our relationship between the sample means and the population mean. Sample proportion, the mean of the sample proportion should equal the population proportion. Standard deviation of the sample proportion should equal, and remember when we found the standard deviation for like a binomial distribution or anything like that, it was p times 1 minus p times n. Well, here we're dividing by that sample size. It ends up being the square root of p times 1 minus p over n. So here's an example for us. Let's say we've got a soft drink cup that you peel off the ticket to see if you win. Proportion of tickets that are winners is 0.25. a total of 70 people. So taking a sample size of n equals 70. We'll get their software drink, and we are going to peel the sticker. So find the mean of those sample proportions. If we took a bunch of different samples of 70, well, the mean of all those sample proportions should be 0.25, just equal to the population proportion. Standard deviation will be p times 1 minus p, so 0.25 times 1 minus 0.25, over n, which is 70. Sample size of 70. Comes up to 0.0518. Notice that is going to be considerably smaller than what would be the mean of individual value, or the standard deviation of individual values. The standard deviation of individual values would be the square root of n times p times 1 minus p. That would be 3.6, well, 3.623. Notice the standard error, or the standard deviation of the sample proportions, is much, much smaller than that. So our central limit theorem can be used to find probabilities for proportions, just like we did for means. So again, looking at our curves, the larger our sample is, the more normal the curve gets. Distributions of p are almost always normal anyway, but so now in this example, p of 0.5, sample distribution of p hat is somewhat close to the normal, even for small samples. The reason for that is because the distribution for p is normal no matter what. When p is close to 0 or close to 1, the larger sample size is needed before the distribution of p is close to normal. So this is what this is saying is when p is 0.5, this distribution is going to be close to normal, even for really small samples. But if p is really close to 0, that means it's going to be really skewed like this. Well, we're going to have a larger sample to make that even out into a normal curve. Or if p is really close to 1, so it's going to be skewed like this. Again, we need a much, much larger sample to make that closer to the normal curve. Common rule of thumb is we can't just say a sample size of 30 here, because it depends on how close to 0 or 1 that p is. But we never, ever use the central limit theorem unless n times p is at least 10 and n times 1 minus p is at least 10. So here p of 0.5 is going to be the same no matter what. So n times 0.5 has to be at least 10. I could solve that. Dividing by 0.5 would give me n has to be at least 20 here. So this is just summarizing that. As long as n times p is at least 10 and n times 1 minus p is at least 10, then the mean of the population, or the mean of the sample proportions, should equal the population proportion. And that standard deviation of the sample proportions should equal the square root of p times 1 minus p over n. So again, our procedure for finding probabilities, check. We got to make sure that we can use the central limit theorem, make sure that np and n times 1 minus p are both bigger than 10. Find the mean of the sample proportions and the standard deviation of the sample proportions. Again, using those formulas that we just saw back here. Next, sketch the curve and shade in the area to be found, and then find that area we use the calculator or the tables. So in this example, according to Summit Entertainment, 80% of the audience for opening weekend in the movie Twilight was female. So for random sampling of 100 members of the audience were sampled, what is the probability that the sample proportion of females is greater than 0.85? So first we need the mean, well, 0.8. The mean of the population proportions, or the sample proportions, is going to be 0.8. The standard deviation of the sample proportions is going to be square root of 0.8 times 0.2, that's just 1 minus 0.8, over 100. So second square root 0.8 times 0.2, that's 1 minus 0.8, divided by 100. 0.04. So now we need to find that probability of being greater than 0.85. So, second distribution, normal CDF. Our lower limit is going to be 0.85. Our upper limit will be positive infinity. Our mean is 0.8. Our standard deviation is 0.04. I could have entered that whole expression in there again, the square root of 0.8 times 0.2 divided by 100. That would work. So I hit enter here and I get 0.1056. That's not unusual. Let's take a look here. They're showing you to draw the curve greater than 0.85. They also get 0.1056 as their probability. Another example, 2008 presidential election. 53% of the voters voted for Barack Obama. If a sample of 75 voters is polled, would it be unusual for 40% of them to have voted for less than 40% to have voted for Barack Obama? I'm going to put this right in the calculator. Rather than finding the mean and the standard error, second distribution, normal distribution. So we're going less than, so negative infinity to 40%, so 0.04, or 0.40, I should say. Just 0.4 we're going to put in there. The mean should be the population proportion of 0.53. And our standard deviation, we're going to put in right now, second square root, 0.53 times, parentheses, 1 minus 0.53, parentheses, divided by the sample size of 75. The reason I chose to enter it this way is because you can see they got an ugly decimal here when they tried to calculate that standard error, that standard deviations of the proportions. By doing it this way, it puts it all in there for me. 0.01204 is what I'm getting for a probability. So that would be unusual. It's less than 5% or 0.05. Let's see how they came out. They get the exact same answer. They just had to divide out that square root and type it back in the calculator. My way is much more accurate. You're avoiding that round off. But anyway, we get the same result. So in this section, we looked at the sample distribution for population proportions and all the notation. We made the sample. We constructed samples. We found the means and the standard deviations and variances. And then we used that along with the central limit theorem to compute probabilities for sample proportions. That is the end of section 6.5 or 7.5. So I'm going to pause for a second to pull up my next PowerPoint. Okay, so for our last section here, we're looking at assessing normality. The key when we're and there's a lot of different tools you can see here for assessing normality, and most of them involve judgment. Making a judgment to see if you think it looks close to being normal. So dot plots, box plots, histograms, stem and leaf plots, those are all going to be a visual thing to see if it looks approximately normal. The quantile plot, normal quantile plot, is a little bit more detailed. We'll take a look at that in just a minute. So using dot plots. Now, it's important to see that in any of these methods, we're not looking to prove exactly whether it's normal or not normal. We're just seeing if it's approximately normal or not. So that's one of the things they're warning here is we are looking to see if it's not saying it's exactly normal, we're just looking to see if it's approximately normal. It's more important for small samples than for large samples because we saw if a sample gets more than 30, the distribution of the means or the proportions is going to become normal no matter what. So if we're looking at small samples, it's when it's more important to assess that normality, because if it's not a normally distributed population, in the small samples, their means are not going to be normally distributed and their proportions won't be normally distributed. So there are no hard and fast rules. The second you find a hard and fast rule for this, or try to make a hard and fast rule, I will find exceptions for it. Just no way to have this rule that if you do this and get this value, then less than this value is normal, greater than this value is not, or the other way around. It just cannot be done. So we will reject the assumption that a population is approximately normal if it has any of the following. So this is important here. If it contains an outlier, so one number that's way away from the rest. Now again, how far away does it have to be an outlier? It's visual and it's left up to your judgment a little bit. It exhibits a large degree of skewness. Again, well, to some people that might be a large degree of skewness because it's tipped off to the side a little bit. Is it too skewed or not too skewed? It's hard to judge. If it has more than one distinct mode, that is a little bit easier. But again, is that saying it has a second mode, or is that just a spot of data missing in the curve? So again, it's not hard and fast. It's not. Two people might look at it and apply a slightly different standard to it and come up with different conclusions. So if the sample has none of the preceding features, we will treat it as though it's approximately normal. So dot plots. Remember the dot plots? We had the number line and put the dots above it like this. Well, here, because it's a small sample, no values are repeated. So what we're looking at is how they are spaced. If they are normal, they should be slightly more concentrated in the middle and slightly more spread out on the sides. Now this one here is, those are kind of tight on the edges, but these are spread out on this side, kind of concentrated in the middle. These are almost evenly spaced across here. Since it does not show a large degree of skewness, it's not like highly concentrated on one end or the other. So it doesn't show a degree of skewness. There's no values that are way out there, so there's no outliers. Again, I don't see any mode. Remember, a mode on a dot plot would consist of having a bunch of dots all in one spot, or two dots repeated. But just a bunch of dots all together, that would indicate a mode there. So if we had a bunch of dots gathered together there, that would be a second mode. Well, this does not have any of that. So this appears to be, we can't conclusively say it's not normal, so we're going to treat it as though it is normal. Now, however, here we've got this recent health fair. We found the pulse rates for people. This one, I would say that is an outlier. At the very least, it's highly skewed, like that. Extremely highly skewed, very much so. So this would not be approximately normal, where we're not treated as approximately normal. If you use a box plot, it's the same thing. Remember, in a box plot, each section of the box plot represents 1/4 of the data. So if the sections are about the same size like they are here, that's saying the data is pretty evenly spread out across the distribution. For a normal distribution, remember, it's a little bit more concentrated in the middle. So the boxes in the middle will be a little bit smaller. The whiskers on the outside a little bit longer. Like that. That would be closer to a bell curve. So looking here, we take these values listed up here. We find their 5-number summary. Remember, you have to find the minimum, Q1, median, Q3, the maximum. Then you have to find those boundaries, those limits. Let's see if there's any outliers. There's no outliers because an outlier, of course, would be represented by an X or a star outside one of the whiskers. There are no outliers here, so that's already determined. So with a box plot, determining whether there's an outlier or not is a little bit more straightforward. You're not just looking to see how far it is away from the other points. But you do see here this piece is a little shorter than that one. This is a little shorter than that one. So this is a little bit skewed. Something like that maybe. But is it a lot skewed? Well, we're saying here that it's not a lot of skewness. It's slightly skewed, but not huge. So no outliers, not bimodal, or no obvious second mode. With the box plot, the mode is a little bit more difficult to see. So we're going to treat this as approximately normal. This one, however, has two things. One, it does have an outlier down here. And two, this is much shorter than that. So it's very, very skewed in its distribution. Histograms. Histograms are the same way. A good histogram for a good set of data, if you follow the bars, you can almost draw a bell curve through the top of the bars. This one here, again, boy, different people might look at it and say, I don't think so, but it's relatively close to bell shape. Not highly skewed, but there are points out on the edges out here that, but the reason this one's not highly skewed is that, yeah, there's a big bar here, but there's also a big one over here to kind of set it off. Could you consider this one an outlier? Well, it's only one spot away, so it's away from the other data, but maybe not quite far enough to be called an outlier. So this one we would say is approximately normal. So you can see here the subjectivity that comes into this. This one looks like it's got some issues. It doesn't look real close to a bell curve, but it's not way, way out there. There's not, you know, a bar way out here all by itself and empty ones in there, or not like a huge skewness. I'll show you in this next example a huge skewness. This one is obviously skewed. It starts and goes down. It's giving you that exponential curve almost, negative exponential curve. That is definitely skewed and definitely would not be treated as approximately normal. Stem and leaf plot. Well, stem and leaf plot is going to look a lot like a histogram just set on its side. You can see here, there's my curve going through the top of those bars. So if I just twisted that, you know, it looks like our bell curve, or if I take the size of these rows of numbers, you basically get the bars of a histogram. So that stem and leaf plot is basically just a histogram, just set on its side. So it's the same type of thing. That one is definitely looks approximately normal to me. Normal quantile plot. I guess they're not going to show us an example that's not, but it's the same thing that you get for a histogram. You can see this one's obviously skewed. For a stem and leaf plot, if you had one, for stem and leaf, if you had one that was, you know, like this, that would obviously be skewed or whatever. Or if you had like numbers here and here and here, and it had like 2 or 3 blank rows, and then had just a number or two out here, then you'd have outliers. So then obviously you'd not be able to assume it's approximately normal. The normal quantile plot requires a little bit more work. Our first step for the normal quantile plot is to put them in order from smallest to largest. Now then we're going to look at how many there are. N equals 5 here. So we're going to use that to assign them z-scores. But we're going to assign them z-scores from, sorry, not z-scores, we're going to assign them values from 0 to 1. And we're going to evenly space them from 0 to 1. So here, n equals 5. So we're going to n equals 5. We're going to start, the first one is going to get the value, the formula is 1 over 2n. So if n equals 5, the first one's going to be 1 over 2 times 5, or 1/10. Well, that's 0.1. The second one is going to be 3 over 2 times n. 2 times 5 would be 3/10, or 0.3. Then 5 over, and then so on, until you get up to the last value. So you can see these are equally spaced. They're all 2 units apart, or sorry, 2/10 apart, I should say. And then they're centered. They're both a 1/10 away from the end of that interval, from 0 on the bottom end and from 1 on the top end. Once we've assigned those values, then we find z-scores that correspond to them. We're looking at the table now, doing an inverse normal here to get a z-score. So if this were on the calculator, I would do so these are representing the probabilities. A probability of 0.1, if we're looking at the curve. Here's my bell curve. 0.1 probability would be an area of 0.1, which would build up to a z-score here. We're finding this z-score. So in the calculator, we're going to do an inverse normal, second distribution, inverse normal. We're going to put in that probability of 0.1. Remember, if we don't put in the mean of 0 and standard deviation of 1, the calculator is just going to assume it. So that'll give us a z-score of negative 1.28, which is what we have right here. For the 0.3, second distribution, inverse normal, 0.3. Negative 0.524. Negative 0.52 is what goes in there. Then 0 for the 0.5. 0.5, half, probably 0.5 would be at the middle of the curve. That's going to be at 0, or the mean. Remember, percent of normal, the mean is 0. And then the same going up. So we get all of those z-scores that correspond to these probabilities. So 0.9 would be up here, where this probability of this area is 0.9, finding that z-score. So we've done the inverse normal. So it is just inverse normal of our AIs here. That gives you the z-score for each. Now what we're going to do is we are going to plot its value down here, the actual number now. So this was 3, and it came up with a z-score of negative 1.28. This was 3.3, had a z-score of negative 0.52. We plot those points. This was 5 something. Where was our original list? That was 4.8. That had a z-score of 0. So that was up there. 5.6 had a z-score of positive 0.52, and so on. If these are approximately linear, now we draw this line through here the best we can, and we can see the points are not too far away from it. These two look like they're a ways off of it, but they're not too far away from it. So we would go ahead and assume this is approximately normal. So the normal quantile plot feels better because we're doing all these calculations. Until you get to this last step where let's draw a line through it and see what it looks like. I mean, it's not hard and fast. I mean, you're looking at it. Some might say, yeah, this point is too far off the line here, so I might not want to do it. But this one I would still say is approximately normal. Now this next example, here the points obviously curl like that. That I would say is not approximately normal. Now your calculator will do a normal quantile plot for you. First thing we have to do in the calculator is enter the data. So I'm going to clear this out and go to stat. So, sorry, not second. No, stat, edit. Got my lists all cleared out. So I'm going to go back up to this slide here and put these in. So 3.0, 3.3, 4.8, 5.9, and 7.8. So I've got them all entered. We'll get out of there. I'm going to go to my stat plots. So second, stat plots. I'll make sure plot 1 is turned on. So I'm going to hit enter to turn on plot 1. It's on. I'm going to go down here and I'm going to select. Oops, so I have dot plot, I have line plot, I have histogram, 2 different types of box and whisker plot. This is my quantile plot, normal quantile plot. It's not labeled, but that is the one you want right there. So you select enter. My data is in list 1, so I'm going to leave that. Data axis goes on the x-axis, so I put my quantiles on the y. Whatever thing I want to mark it with, that's fine. So now I'm just going to hit the zoom button here, and zoom 9 is the stat zoom. Usually it works best. And you can see there's those points that we had. That is identical to this graph we had right here. See all those points are going across the line. If I drew a line in right across there, is exactly what we have down here. Now for this one, they're going to do, they did this big data set. Let's go ahead and try that one. Why not? So I'm going to go to, oops, let me do a second. Stat, edit, edit. So list 1, I'm going to clear it out. I'm going to enter, make sure I got all these in here. Yep. So I'm going to enter 61, 60, 60, 68, 63, 63, 94, 66, 65, 98, 61, 71, 74, 63. See, it looks like I got 14 values in there so far. 66, 61, 61, 65, 72, and 85. That should be 20. Yes, it's saying L is 20. L1 is in 21. There's nothing in 21, so there are 20 values there. So go, my stat plot should already be all set. Just double checking it. Plot 1. All my settings are still there, so zoom 9. There you go. I get this. That's obviously curved. I would not call that straight line and linear at all. So that's definitely not approximately normal. And that's the calculator doing all that. So here we looked at different ways of assessing normality. The dot plots. Again, make sure there aren't any big bunches that are not in the center. Make sure there are no dots that are way away from the others. The box plot, comparing the size of each of those 4 sections, and also make sure there's no outliers. The histograms, again, just the shape of the bars. If you draw a curve through the top of the bars, does it look close to that bell curve? Stem and leaf plot, it works just like the histograms do. Just turn on its side. And the quantile plots to see if it's approximately linear in the quantile plot. So that is it for week 8. If you have any questions, please let me know. Otherwise, you all have a great week.